Hello, this is Jack Jackson. In this video we're going to do a real-world example of applying some of these things that we've been talking about probability distributions, and put this in the context of a real-world problem. So a distribution like this, which is actually an exponential distribution where lambda is 0.3, can represent something like the density function for duration of telephone calls. So within a certain city, the duration of telephone calls is modeled well by this PDF of x is 0.3 e to the negative 0.3x, where x represents the duration in minutes of randomly selected call. Now, even though it didn't say it here, we notice that x cannot be negative because we cannot have a call of negative length. So really the PDF is 0 to the left of 0, left of the y-axis, and then for positive x's, this is where this formula goes. So the appropriate domain, really, the practical domain, is the non-negative real numbers. And so we could graph that, and here's what it looks like. Definitely skewed to the right. Most of the probability is close to 0. Most of the calls are short. Very few that last a long time. Okay, now how do we verify that this really is a probability density function? The first condition is that the probability must be greater than or equal to 0 over its entire domain. Remember, e to any power is positive, so that part is easy. That's positive, and 0.03 is positive, so it's clearly satisfied. And for the PDF is just 0 for x is less than 0, so we can ignore that part. Also, the total area under the curve must be equal to 1. That is, the integral from, well, again, the integral from minus infinity to 0 is just 0. So the integral from 0 to infinity of this function must be 1. We let u be negative 0.3x, du is negative 0.3 dx, and this becomes, put a negative in with the 0.3 and the dx, 0.03, that becomes du. This is e to the u. To balance this negative 1 that we put right here as part of the du, we put a negative out front. So we have the negative, the integral of e to the u du, and eventually we're going to evaluate from x equals 0 to x approaching infinity. And of course the antiderivative is just e to the u, but we still have the minus out front. So it's minus e to the negative 0.3x from 0 to infinity. If we plug in 0, we get e to the 0, which is 1. And that's minus, and then a negative makes plus 1. And this first part is going to give us a limit of 0. So, in fact, that we do get 1. We can sort of check this with our calculator, but on a TI-84 calculator, for example, you can't put in infinity here, but we could put in something large, like say 100, and it turns out by that time the calculator is already approximating that to be approximately 1. What percentage of calls last between 2 and 3 minutes? So we have a PDF formula. That probability is given by integrating our PDF from 2 to 3, and so we can work that out here. Again, it's the same antiderivative, minus e to the negative 0.3x. We just evaluate from 2 to 3, plug in the 3, plug in the 2, and work it out. So if we get something like this as an exact value of that integral, but of course this is a real-world problem. We want a decimal value, which turns out to be about 0.14 something, or about 14%. Of course, since we only need a decimal value, we could have just done this in a calculator by doing function integrate of our PDF with respect to x from 2 to 3 and get the same number. Graphically, that's represented by the area under this PDF curve from 2 to 3 down to the x-axis, so that shaded area. What's the mean of the distribution? We take the PDF times x and then integrate that. So we're integrating x times that PDF of x. To do this exactly, we would actually need to do this by parts and evaluate that improper integral using a limit to get the, because of the infinity there. If we integrate this from 0 to 100, we see that we get 3.3 repeating, which is 10/3. And so it looks like that might be the case. In fact, I can actually apply a result that we've already done, because in our previous video, we actually computed that the mean of an exponential function, if you look here, again, integrating by parts, like I said, is 1 over lambda. So applying that result, we see that it should be 1 over 0.3, which is 10/3, or 3.3 repeated. So that actually works out just fine. What's the CDF? Again, we can work this out. Here's the antiderivative here, but evaluating it from 0 to x. And we get e to the 0 is 1, so this is 1 here. And then we get minus e to the negative 0.3x. Or, again, we can appeal to what we've already done earlier when we found the CDF in general of a exponential function. In a previous couple videos back, we did that right here and found the formula for the CDF in general is 1 minus e to the minus lambda t. Our lambda is 0.3, and so we can apply that result if we remember it, or we could just do the work again like we just did right here. What's the median distribution? To get the median, we first must find the formula for the CDF, which we have. So this is CDF of x is 1 minus e to the negative 0.3x. Put in the median there. I'll call it or mu tilde, either one. Plug that in for x, and then the y then is 1/2 out of the integral. Okay, or the y value. 1/2 is this integral, but it's also the CDF of this mu tilde, the median value that we're looking for, not the mean, but the median. So the median value here, we plug in the CDF formula, we get 1/2. So we just solve this. Let's see, subtract 1/2 from both sides. We get 1 minus 1/2 is 1/2, and then we get e to that power. Take a logarithm, and we get 10/3 log of 2. Once again, we did this earlier in general and found that the mean of a exponential function is just 1 over lambda. I'm sorry, did we do the median? I don't know if I did the median. Yeah, here I did the median. It's natural log of 2 divided by lambda. I did that in general earlier. For a general lambda, you can follow the details in an earlier video, and that's 1 over lambda is 10/3 times natural log of 2, or approximately 2.3, whatever. I can get the decimal approximation, and we can visualize what's going on by graphing the CDF, the 1 minus e to the negative 0.3x, which is this curve here. Again, this formula applies from 0 to the right. This increasing concave down function, which has an asymptote of 1 on the right and starts at the origin here on the left. And we graph the horizontal line y equals 1/2 and see where they cross by doing a calc intersect. We'll get at least the same decimal approximation for that value. That's essentially how you do an inverse an inverse probability function. In our next video, we'll talk a little bit about the normal probability function, which is a very, very important